Are going to do problem 11. It says a sigma plus particle with a total energy of 3000 mega electron volts decays into a neutron and a pion. Determine the energies and momenta of each particle. So this is a good example of an elastic. It's not really a collision, but it's an elastic we can call quote-unquote collision problem. It's going to conserve momentum and kinetic energy. Okay? And we're also applying this relativistic problem to particle physics because this is a typical kind of particle physics decay. So you can watch my videos on particle physics on the addendum questions section, and you can see that sigma, one of the modes of decay, is into a pion and a neutron. So this is an accepted mode of decay. Sigma plus decays into a neutron plus a pion plus. Okay? So one of the things we're going to have to look up for this one of the things that you have to look up for this kind of problem is you have to look up what is the rest mass of each particle, right? So the rest mass of the sigma plus happens to be 1260 mega electron volts per c squared. That's the rest mass. So oftentimes for small particles, instead of giving the rest mass in kilograms, we give it in units of energy divided by c squared. Remember, I said E0 is equal to m0 c squared. So if I want to say the rest mass of something, I can state it in terms of how much energy it contains divided by c squared. I can also say the rest energy of the sigma is 1260 mega electron volts. Okay? So either way, depending on the data table, they will either give the rest mass or the rest energy. Now, in this case, we see that it has a total energy of 3000 mega electron volts. So that means it is traveling with a certain velocity. Okay? So the sigma particle, here is the sigma, it's coming with a certain velocity, initial. And then all of a sudden it decays into a neutron and pion. So let's say the neutron happens to be going forward with a velocity v2, and then the pion, pi plus, happens to be going backward with a velocity v1. So the momentum after the collision and the sum of the kinetic energy after the collision must equal to the original kinetic energy of the incoming particle, right? So let's go about now solving this. What else do we need? We need to know the rest energy or the rest mass of the neutron and the pion. The neutron turns out to be about 1080 mega electron volts per c squared, and the pion comes out to be 720 mega electron volts per c squared. We have to impose momentum conservation on this problem and kinetic energy conservation, right? So what are we going to say? So we're going to say the momentum initial is equal to the momentum final total. Gamma initial, m0, v initial. And then for the final, it has two gammas. So we could say gamma 2, and then the mass of the neutron, the rest mass of the neutron, times v2, right? So that's going to the right. And then I have to subtract from it gamma 1, the rest mass of the pion. So I will write m pion rest mass times velocity 1. Right? The rest mass was equal to 1260 mega electron volts divided by c squared, and then v initial, and then gamma 2 we don't know, and then mass of the neutron was equal to 1080 mega electron volts per c squared, v2, minus, which we don't know what it is, and then mass of the pion, that's equal to 720 mega electron volts over c squared, and then v1. Now notice mega electron volts over c squared cancels. It cancels, so again we don't need to put what c squared is, right? Everything cancels, and we end up with this equation. 1260 v initial, gamma initial is equal to 1080 gamma 2 v2 minus 720 gamma 1 V1. Okay? So for now, let's keep that like that. We also need now kinetic energy conservation. That's equal to the kinetic energy final of the neutron plus the kinetic energy final of the pion. Okay, so now what was the kinetic energy initial? Well, remember that the problem told you the total energy of the incoming sigma particle was 3000 mega electron volts. So the total energy initial is equal to the rest energy plus the kinetic energy initial. So total energy was 3000 mega electron volts. The rest energy is 1260 mega electron volts. And therefore the kinetic energy initial we already know. The kinetic energy initial is equal to 1740 mega electron volts. This one is actually mega electron volts. It's not divided by c squared, right? So that's the incoming kinetic energy, 1740 mega electron volts. Okay, the final kinetic energy of the neutron, so that's going to be, remember the neutron is what we called gamma 2, so that's going to be what? Gamma 2 minus 1. Remember, what was the equation for kinetic energy? Let's write down the general equation. Kinetic energy, gamma minus 1 mc squared. Right? So gamma 2 minus 1, mass of the neutron, c squared, plus the kinetic energy. So remember, for kinetic energy, you're always adding it. It doesn't matter that one goes one direction, the other one goes the other direction, right? You have to add the kinetic energies. Plus gamma 1 minus 1, the mass of the pion, rest mass, c squared. Okay, so 1740 mega electron volts. Gamma 2 we don't know. Mass of the neutron was 1080 mega electron volts divided by c squared. 1080 mega electron volts over c squared times c squared. What happens? C squared cancels, right? C squared. And then gamma 1 minus 1. And then mass of the pion. And then that's going to be 720 mega electron volts over c squared times c squared, mega electron volts cancels. So the whole point is this becomes something that is unitless. So it becomes 1740 is equal to 1080 gamma 2 minus 1. Okay, so the minus 1 is coming from here. And then plus 720 gamma 1 minus 1. Okay, so now what are we going to do? Well, we could multiply this in and then gather like terms and take it to the other side. So I can say 1740 is equal to 1080 gamma 2 minus 1080 plus 720 gamma 1 minus 720. And then, okay, so what is that going to equal? Well, we essentially have now two equations. Okay? I have 3540 is equal to 1080 gamma 2 plus 720 gamma 1. And then my other equation are 1260 V initial gamma initial is equal to 1080 gamma 2 V2 minus 720 gamma 1 V1. Other thing that we need to do is we need to figure out what this term is. Okay? Do we have to actually find out what the V initial is, what the gamma initial is? Basically, this one is what? This stands for what is the initial momentum of the incoming object. So it seems like, whoa, we might have to find out what the V initial is. The problem didn't give us that. The only thing the problem gave us is the initial kinetic energy was 1740 mega electron volts. So we don't know what its initial velocity is. Therefore, the question is, do we need to find out what the V initial is and what the gamma initial is, or is there like a shorter way? The answer is there is. Remember the last equation I gave you in the previous problem, the last equation of dynamics is that the total energy squared is equal to PC squared plus the rest energy squared. Okay, so the total energy squared, that's equal to 3000. So 3000 mega electron volts squared is equal to PC squared plus the rest energy. The rest energy is equal to 1260 mega electron volts. So I know that the sum is equal to 3000. So 3000 is equal to PC squared plus, and then the rest energy is equal to 1260 mega electron volts squared. So basically I do 3000 squared minus 1260 squared. Well, what am I going to do? I can square root both sides, square root this, square root this, square root this, and what do I have? Well, I basically have a smaller number, 2722.572 mega electron volts, okay, is equal to PC. And then if you divide this by C, it comes out like this. So the linear momentum is equal to 2722.572 mega electron volts divided by the speed of light. So that's actually, I can put it right here. Okay? The only thing you have to be careful for now, since we changed this, let's be careful for the units. So remember, this was mega electron volts divided by C, right? What were these original units? It was mega electron volts divided by C squared. It was mega electron volts divided by C squared. So mega electron volts, mega electron volts, mega electron volts cancel. If I multiply everything by C squared, the C squared cancel, I end up with a C on the top here. So just to make sure, if you're going to do it this way, you want to put the initial momentum, you put 2722.572, and then you have to put an extra C there, because that comes from the C squared and the C squared on the denominator here, which comes up to the top here and becomes a C. So now here are my two equations. So this looks quite different than elastic collision problems in regular mechanics. In regular mechanics, you would have a term such as V squared, and then you would have a term such as V, you would substitute and stuff like that. Here it looks quite different. You have gamma 2, you have a gamma 1. So in the energy equation, you don't really have that square thing, and then you have gamma 2, gamma 1. So what are we going to do? Now remember, gamma 2 and V2 are related. Okay, they're not actually different things. So how do we solve this best? What I would like to do in this case is have just one equation, and then in that one equation I want to just have gamma 1 or gamma 2. So I can do a substitution. I can say gamma 1 is equal to 3540 minus 1080 gamma 2 divided by 720. Take that gamma 1 and put it into here. 572C is equal to 1080 gamma 2 V2 minus 720, and then I'll put this expression, gamma 1, so I'll put, let me just erase this here, so I'll put gamma 1 expression, 3540 minus 1080 gamma 2 over 720, okay? So 720, that's here. Gamma 1, I replaced it by substituting from this equation into that equation, and then I multiply this by V1. Okay? Well, one of the things that happens, the 720 and the 720 cancels. So you get rid of that. So remember, you have to be able to distribute. So it's better if I write the V1 here, you can visualize better. And so the number 720 canceled with that number 720. So distribute the V1 times this, 3540 V1, and then minus V1 times that, it gives you plus 1080 V1 gamma 2. Okay.